Hello everyone, welcome to lecture 4 of our course on processing in memory. Today we are going to continue talking about the UPMEM PIM architecture that we started to introduce in the previous lecture. We are going to talk in more detail about this architecture, explaining the microbenchmarking that we did to analyze and understand this system. Remember that the UPMEM PIM architecture is based on DDR4 DIMMs. Inside on each DIMM, we have multiple PIM chips or UPMEM PIM chips, and inside the PIM chips, we have DRAM memory banks and small processors called DPUs. Remember as well the system organization with a host CPU that still has access to conventional DRAM, the main memory, but also this accelerated DRAM that is a PIM-enabled memory. Inside each PIM chip, remember that there are 8 DRAM memory banks called SIMDRAM banks and 8 DRAM processing units or DPUs. As you can see, the DPU pipeline has access to actually 2 SRAM-based memories. One is for instruction, and the other one called WRAM is a scratchpad for operands. It's sort of a software managed cache. We are going to talk in more detail today about all these different components. So let's talk about the microbenchmarking of the UPMEM PIM architecture. Remember that inside the PIM chip, there are these 8 DRAM banks called SRAM of size 64 megabytes. We access these SRAM banks through a DMA engine, and with this DMA engine, we can move instructions to the 24 kilobyte IRAM, or we can move operands between the SRAM and this 64 kilobyte scratchpad called WRAM. The pipeline has access to the IRAM to fetch instructions and also has access to the WRAM to read input operands and write output results. So we are going to first start analyzing what's the arithmetic throughput that we can achieve in this pipeline for different operations and data types. Because the operands originally reside in the WRAM in the typical operation of the DPU, we are going to consider the accesses to WRAM before and after performing the actual operations on the ALUs. In the previous lecture, we already saw this code with an example microbenchmark that we use to measure the arithmetic throughput. In particular, this one is for 32-bit integer addition. Remember that here we can see a for loop, and the for loop translates to this move instruction to initialize the index, and then the add instruction for the increment of the index, and finally the conditional jump to check whether we reach the end of the loop or not. We have accesses to WRAM. First of all, we need to calculate the address and then load one word from the WRAM into a register. Then we have the addition operation, the addition instruction itself, and finally we store the result to WRAM. So let's take a look at the arithmetic throughput using this microbenchmark and similar microbenchmarks for different types of operations and data types. Here on the slide, you can see in 4 plots, and for each plot, we have the arithmetic throughput in the y-axis in mega operations per second, and the number of tasklets between 1 and 24, that is a maximum number of tasklets. And we are going to observe how the arithmetic throughput changes for different operations, data types, and numbers of tasklets. So let's start with the integer, 32-bit integers. These are the results for addition and subtraction, and these are the results for multiplication and division. And here you can see the results for the rest of data types, 64-bit integers, float, and double. The first observation in these plots is that the arithmetic throughput of the DRAM processing unit saturates at 11 or more tasklets. And this observation is consistent across data types and operations. The number 11 is related to the number of 4-time pipeline stages. It's just that the last 3 stages can overlap with the first stage for one particular tasklet. Another observation is that the addition and subtraction for 32-bit integers is about 17% faster than the addition and subtraction for 64-bit integers. We try to explain the reason for this difference in the peak throughput. Observe, first of all, that the peak throughput happens at 11 tasklets, and at that point, one instruction retires every cycle when the pipeline is full. We estimate the arithmetic throughput using this expression, where we divide the frequency of the DPU by the number of instructions that we need for a specific operation. In this case, we are talking about integer 32-bit or 64-bit integer addition and subtraction. If we observe the code, the two microbenchmarks for 32-bit integers and 64-bit integers, we see that they are very similar. But there is a key difference, is that there is one more instruction, this add with carry, because the architecture supports 32-bit operations, but we can also compile, so the native ISA is 32 bits, but we can also compile for 64-bit operations. And basically for the addition or of integers, we need the first add here to add the lower 32 bits of the 64-bit element or value, and then we use this add C instruction for the upper 32 bits. So in total, we need 6 instructions for the 32-bit addition and subtraction, and 7 instructions for the 64-bit addition and subtraction. And this is basically what explains the performance difference. With 6 instructions, the resulting throughput is 58.33 mega operations per second, while for 7 instructions is 50 mega operations per second. This assuming a frequency of 350 megahertz, that was the frequency of the UPMEM system that we use for this analysis, or the DPUs that we use for this analysis. Another observation is that there is a significant throughput difference between integers and double. And in fact, there is also a significant performance or arithmetic throughput difference between addition and subtraction of integers and multiplication and division. There is a reason for that. The thing is that the DPUs only have native support for 32-bit and 64-bit integer addition and subtraction. The other operations, multiplication and division of integers and floating point operations, are emulated by the runtime library, and that results in significantly lower throughput. In the extended lecture, the extended version of this lecture, you can also see some analysis of the access to the WRAM from the pipeline, measurements of latency and bandwidth. The key summary here is that when the pipeline is full, we can read 8 bytes per cycle. When I mean pipeline full, mean that there are at least 11 tasklets. That is the number of tasklets that we need to achieve the highest performance in the pipeline, as we have just seen. We are going to put a little bit more attention right now to our measurements on the MRAM latency and bandwidth, which basically is the data movement between the DRAM bank and the WRAM, the scratchpad memory. In our analysis of MRAM bandwidth and latency, we wanted to measure latency and bandwidth, especially bandwidth, for different access patterns. But the first thing that we do is measuring latency of a single DMA transfer. There are 2 types of transfers, MRAM read and MRAM write, depending on whether we are moving data from the MRAM to the WRAM or vice versa. We also did analysis of the bandwidth using the stream benchmark. We are going to talk in a minute about the stream benchmark and its 4 different versions. And we also studied strided access patterns and random access patterns. So let's start with the latency of a single DMA transfer. Here in this plot, you can see the bandwidth and the latency for both MRAM read and MRAM write for different data transfer sizes, between 8 bytes, that is the smallest, and 2048 bytes, that is the maximum. We estimate the bandwidth from our SIMDRAM latency measurements using this expression. And one first observation here is that we can model the SIMDRAM latency with a linear expression, something like this, which, as we can see, fits pretty well our measurements. The model that follows this linear expression is this thin black line. From our measurements, we can already observe that this beta equals 0.5 cycles per byte. And that's basically the bandwidth or the theoretical maximum bandwidth that we can have between the SIMDRAM and the WRAM. And that translates to 700 megabytes per second for one DPU running at 350 megahertz. So one first observation about these latency measurement results is that the bank access latency increases linearly with the transfer size, as we can see in the plot following this linear expression here, and that the maximum theoretical SIMDRAM bandwidth is 2 bytes per cycle. Let's now take a look at some of the results for the stream benchmark. Before we look at the result, let me remind you what the stream benchmark is. Basically, the stream benchmark performs stream accesses or sequential accesses where we are copying the contents of one input array, in this code called buffer A, into one destination array that is called buffer B here. This simple code corresponds to the copy benchmark, the stream copy benchmark, because in the DPU we have the data originally in SIMDRAM and we need to move data to WRAM in order to be able to operate with it. What we first do in this stream benchmark, or in this stream copy benchmark, is to read data that basically we move a large chunk of data between the SIMDRAM and the WRAM. Then we perform the streaming accesses in WRAM, copying buffer A, that is in WRAM, into buffer B, that is also in WRAM. And finally, we write the contents of buffer B into the corresponding destination in the SIMDRAM. There is another version of copy that is called copy DMA. In this case, we don't explicitly access the arrays in WRAM. We just move one chunk from SIMDRAM to WRAM and then directly write it back from WRAM to SIMDRAM. For the other stream benchmarks that are add, scale, and triad, the operation is going to be very similar to the copy benchmark. The key difference is that they won't be just a single copy, but in add we have two input arrays that we copy from. So we read one element from one, read the other element of the other one, add them, and store in the destination array. In scale, we have one input array. We multiply the elements by a constant, and then we write to the output array. And in triad, we have multiplication and addition. Let's take a look at the results of the stream benchmark. First of all, the copy DMA benchmark. Notice here that we have in the x-axis a number of tasklets between 1 and 16, and in the y-axis the sustained SIMDRAM bandwidth in megabytes per second. These are the results for the copy DMA benchmark. As we can see, we are very close to the maximum theoretical bandwidth of 700 megabytes per second. We are in around 624 megabytes per second, and this translates in about 1.6 terabytes per second for a full UPMEM system with 2,556 DPUs. This bandwidth can be higher if you have more DPUs, and can be higher as well if these DPUs operate at higher frequency. Remember that these measurements were done in a system where the DPUs run at 350 megahertz, but the newest DPUs run at a frequency of 425 megahertz. And one observation here for the copy DMA benchmark is that the bandwidth saturates at 2 tasklets and then it's flat. In reality, this copy operation is being done through the DMA engine, and this DMA engine is able to only sustain a single transfer at a time. However, if you have 2 or more tasklets, we guarantee that there will always be one DMA request in queue to keep the DMA engine busy. And this is why we see a slightly higher bandwidth for 2 tasklets than for 1 tasklet. Regarding the copy and add benchmarks, we see that they saturate at 4 and 6 tasklets respectively. However, scale and triad saturate at 11 tasklets. Remember that 11 tasklets is the number of tasklets for which the arithmetic throughput saturates for different operations and data types. So we can observe here that the reason why copy and add saturate with less than 11 tasklets is because the pipeline latency is initially shorter than the pipeline latency is not able to hide the latency of NRAM accesses. So for copy and add, the latency of NRAM accesses becomes longer than the pipeline latency after 4 or 6 tasklets, respectively. In the case of scale and triad, the pipeline latency is longer than the NRAM latency for any number of tasklets, and this is why we see that the bandwidth saturates at 11 tasklets, because the arithmetic throughput also saturates at 11 tasklets. And now remember that this scale and triad use multiplication, and multiplication is pretty costly because it's emulated. So interesting observations here is that there will be workloads where the memory access latency saturates, memory access latency is longer than the pipeline latency, the execution of instructions in the pipeline. And this means that the access to memory hides the execution of instructions in the pipeline. This is a memory-bound workload. There will be other cases where the pipeline latency is larger than the NRAM access latency, and this is a compute-bound workload. As we will see, most of real-world workloads will be compute-bound workloads on this architecture, because in most of the cases, we will have computation that is more complex than just this copy operation or this add operation that we perform in the stream benchmark. In our paper, you can also find, and in the longer version of this lecture, you can also find results for the strided access patterns and the random access patterns. Now, I want to show you some interesting results that compare the arithmetic throughput to the operational intensity. Operational intensity is basically the number of operations that we perform per byte that we read from memory. If you want to take a look at the code, it looks more or less like this. We first copy one chunk of data from the WRAM, from the MRAM to the WRAM, and then we perform a variable number of operations on each element of that chunk of data that is in WRAM. And finally, we write back to the MRAM. The number of operations is given by the number of repetitions of this code. When the operational intensity is very low, that means that we don't operate on all the elements of the vector of the array, and that's in those cases this stride will be larger than 1. So here we are going to see some results. Remember that here we are connecting the arithmetic throughput to the operational intensity. Remember as well that the operational intensity is the number of operations that we perform per byte accessed from memory, from MRAM in this case, and this plot shows the arithmetic throughput in mega operations per second on the y-axis, and in the x-axis we have the operational intensity. So this dot here represents the arithmetic throughput for one single tasklet when the operational intensity is 1/2048. This is pretty low, as you see, because it means that we are only performing a single additions of 32-bit elements, as you can see here, only a single addition every 2048 bytes. So it's a very low operational intensity. When we have such a low operational intensity, it is expected that the MRAM latency takes longer than the access, the latency of access to MRAM or moving data between MRAM and WRAM takes longer than the latency in the pipeline, basically because the number of operations is very, very low. So the result of that, as we have seen in the stream benchmark, is that the performance or the arithmetic throughput saturates at a low number of tasklets. In this case, it saturates at 2 tasklets. And we can see that for higher number of tasklets, the throughput is exactly the same. And this trend remains for longer or for higher operational intensity, as you can see here. And at some point, it will start saturating with 3 tasklets. But we see that for more than 3 tasklets, in this case, for an operational intensity of 1/32, the arithmetic throughput is the same. For more than 3 tasklets, the arithmetic throughput remains the same. And that's going to be the case until we reach this point, 1/4, so 1 operation per byte or 1 operation per 32-bit element, which is 4 bytes, where we see that the arithmetic throughput starts saturating at 11 tasklets, and then it remains flat until for any number of tasklets. In our experiments, we use up to 16 tasklets, as you can see. And this is the same for higher operational intensity. So we can clearly identify in this plot a memory bound region and a compute bound region where arithmetic throughput is flat at its maximum. And there is also a throughput saturation point, that is the operational intensity where the transition between the memory bound region and the compute bound region happens. And one thing that we can observe is that this throughput saturation point is pretty low. It's as low as 1/4 operation per byte for 32-bit integral additions. And in fact, this throughput saturation point is even lower for other operations and data types. So the key conclusion here, the key observation here is that the arithmetic throughput of the DPU saturates at a low or very low operational intensity. And that means that the DPU is fundamentally a compute-bound processor. So we expect that most real-world workloads will be compute-bound in the UPMEM PIM architecture. But this is some analysis that we are going to see in later lectures. So for this lecture, the key takeaway is that there is a memory-bound region and a compute-bound region, and the throughput saturation point, that is the transition between these two regions, is pretty low in general. So we can consider that the UPMEM PIM architecture is fundamentally compute-bound. So we expect that the most suitable workloads are memory-bound on conventional processor-centric systems such as CPUs and GPUs. You can find many more details in our paper, in the Safari Live seminar that where we explain all of the details about this analysis of the UPMEM PIM architecture. But for now, I would like to recommend you the longer version of this lecture that corresponds to a previous semester, where you can find many more details about the microbenchmarking of the DPUs. In later lectures, we will continue talking about the UPMEM PIM architecture, but we will also introduce other PIM devices from Samsung, SK Hynix, Alibaba, etc. So stay tuned. I hope you found the lecture interesting. Please don't hesitate to reach out to me if you have any questions or comments about the lecture and the course. And thank you very much for your attention.